Bismillahirrahmanirrahim, dear students. Assalamu alaikum. My name is Ehsan Elahi. I'm here with a new video. Dear students, we have discussed earlier about FETs, JFET, junction field effect transistor, metal oxide field effect transistor in depletion mode. Today we will discuss about enhancement type MOSFET or E-MOSFET. The E-MOSFET enhancement metal oxide semiconductor field effect transistor is a semiconductor device that is widely used for switching purposes and for amplification of electronic signal. This is also similar to D-MOSFET, which is depletion type metal oxide field effect transistor. But the main difference in D-MOSFET and E-MOSFET is that in depletion type MOSFET channel material is present, but in E-MOSFET the channel material is always absent. Here is the schematic diagram of E-MOSFET. Here we can see the source, drain, and gate, but the channel material here is absent. Here is a SiO2 silicon dioxide layer which acts as insulator or dielectric medium. It sets up opposing electric field within the dielectric when exposed to an externally applied field. Here SiO2 is act as dielectric medium and whole arrangement is placed on p-type substrate. And this is the schematic diagram of E-MOSFET. And this is the symbol of E-MOSFET and channel E-MOSFET. We can see that here the dotted line shows that the channel material is absent. And if we short substrate and source, then we call it three terminal device. Otherwise we normally say that it's a four terminal device, and the dotted line shows that the channel material is absent in E-MOSFET. And this is the description of schematic diagram. Here we can see that here is a drain which is connected to metal contact, which is n-type material, and here is a source which is connected to n-type metal contact. Here is a gate and the channel material is absent from here, and here is the silicon dioxide. The drain and source connected to n-dope region, and the here gate is separated from this material p-type material through silicon dioxide layer, and the whole arrangement is placed on p-type substrate. And here is a schematic of biasing we have applied here. We can see that here the drain terminal is reverse bias and source terminal is forward bias, and this is n-type terminal and which is connected to p terminal of the battery, and source is connected to negative terminal of the battery. And when we apply biasing here, the virtual or induced channel is produced. Virtual channel is present here, and we can say that the channel induces after biasing. And here is the biasing in detail when we have applied the positive terminal to the drain and negative terminal to the source. Then what will happen when we apply the positive biasing here? Then the holes will be repelled from this region and goes towards the p substrate, and the number of electrons from source goes from source to drain, and drain will attract the maximum number of electrons from source, and electrons from substrate will be attracted toward, and electron from here will be attracted toward the channel which is induces after biasing to. When we apply here the positive voltage to the gate terminal, then the number of electron will be attracted towards channel which is induces after biasing. If we talk about VGS and VDS, for VGS is equal to 0 when we have applied no biasing on gate terminal, then the value of current will be 0 and there will be no channel here. And for VDS, when we have applied some positive voltage but VGS is equal to 0, then there will be no current from source to drain. And if we talk about the threshold voltage, here is the level of VGS that result in the significant increase in the drain current is called threshold voltage, or that this is the minimum voltage which causes to turn on the device. At these voltages, the device start working when the VGS is less than, here when VGS is less than threshold voltage, then the value of current, drain current will be 0. And when we apply VGS positive, when the VGS will be positive, then the number of electrons will be attracted from p substrate towards n channel, which induces after biasing, then electron goes from source to drain. Because we have already applied VDS here, the drain terminal attracts the electron from source, and through this mechanism the conduction will occur in E-MOSFET. And when the value of VDS is sometime passive, but if we have VGS is equal to 0, then no channel will be present. And when the VGS greater than VTH, then the device will start working. And is the basic operation, here we can see that the VT threshold voltage equal to 0, then the after this voltage the device will start work. And we can see that the value, as we increase the value of VGS towards positive region, then the source to drain current will increases. And we see that after 3 4 or 5 and up to so on, when VGS is equal to positive V, then the value of current will be 10 milliampere. Here is the graph between VT, where here is the graph between drain current and gate to source voltage, and here is the graph between drain to source voltage and drain current. We will describe after some time in detail about this. And this is the description about the transfer characteristic of device. And we can see that there is a threshold voltage which is 2 volt, and the enhancement type MOSFET operate only in enhancement mode. We can say that when the value of VGS is positive, then as VGS increases, the value of drain current will increases. As we keep increasing the value of VGS, then the current saturates. After some time, we can see here is the saturate the device saturate here at VGS is equal to positive 7, and we can say that device saturate here at VGS is equal to positive 8 volt and the value of current is 10 milliampere. And we can calculate the value of saturation voltage through this formula, which is equal to VGS minus threshold voltage. And these are the transfer curves of the device. As the value of VGS we increase towards positive region in N channel E-MOSFET, then the value of source drain current increases. And we can see that as the value of VGS increases, then the value of drain current also increases. And this is the maximum value of current the saturate after this voltage. And this graph is between current source drain current and VGS. Here is the formula through which we can calculate the value of current. Here ID is drain current and K is constant, and VGS is the gate to source voltage, and VTH is the minimum voltage required to turn on the device. And these are the threshold voltage here. VTH is threshold voltage or voltage at which the most bit turns on and K is constant. And we can calculate the value of K from here as IDS is on, and we can substitute here is a 10 milliampere or 7 milliampere or 4 milliampere current. The value of current it is on own desire, and VGS on these voltage we can use these voltages 3 volt, 4 volt, 5 volt, and VTH are the threshold voltages, and VTH is threshold voltage on which the device start working. And for example, we substitute the value of current ID on is 10 milliampere at VGS is equal to positive 8 voltage. These are the values. ID on is 10 milliampere. Here is ID on value we can use in this formula. When we substitute these values ID on, VGS on, and VTH, here value of VTH is 2 volt, we can calculate the value of K through this formula 10 milliampere 8 minus 2. This is the value of K which is constant. Here is the end of N channel or N type enhancement metal oxide field effect transistor, and it is P channel enhancement type MOSFET. If we say that the schematic diagram is totally reverse here, we can see that substrate is N type, but if we talk about previous some slides, the substrate was p-type, and here is the substrate is n-type. The metal contact that we are using here are p-type, and drain is connected to p-type metal contact, and also here is source is also connected to p-type material. And these are the symbol. The arrow is outward here, and we can see it is a 4-terminal device and it is a 3-terminal device. And these are the transfer characteristics for p-channel enhancement type MOSFET. We can see that in n-channel n-type enhancement MOSFET, we have applied the positive value of voltage, but here we apply the negative value of voltage. When we apply the negative value at the gate, then the number of electron will go against to the channel material and move towards the substrate, and number of holes will go to this channel, and you see the virtual channel here, and we can see this is the graph between drain current and the VGS. As the value of VGS increases towards negative region, then the value of current increases. And we remember that when the VGS less than threshold voltage, then the drain current of an enhancement MOSFET will be zero, and the device will be in no working condition. And these are some characteristics we will discuss here. When the cutoff region, when the value of VGS less than threshold voltage, then the device will be in switch off condition. If we talk about linear or ohmic region, and this region is called ohmic or linear region. When the value of VGS greater than threshold voltage, the device start working, and the value of VDS less than VGS, then there will be a this region. This is called ohmic or linear region. In linear region, VGS greater than threshold voltage and VDS less than VGS, and the transistor will be in constant resistance region, behaving as voltage control resistance whose resistive value is calculated by gate voltage or VGS level. If we talk about the saturation region, after this level, this region is called saturation region, when the value of VGS greater than VTH and the value of VDS will be greater than VGS. In this region, with VGS greater than threshold voltage and VDS greater than gate to source voltage. The transistor is in its constant current region, and we can say it's fully on. The drain current will be maximum with the transistor acting as a closed switch. And these are some regions we have discussed here, and these are the advantages of MOSFET over JFET. We prefer MOSFET in working. The insulated gate in MOSFETs result in much greater input impedance than that of JFET. That's why we use it in amplifier, and it is very easy to fabricate than JFET. And MOSFET have some application. MOSFETs are ideal for use as electronic switches or some common source amplifier, as their power consumption is very small. MOSFET normally consume low power than other BJTs or JFETs. Typically application for metal oxide semiconductor field effect transistor are in microprocessor. We can say the microprocessor is a brain of computer which do all the processing computer, and we make memories through MOSFETs like RAM, ROM or hard disk and calculator, and also logic CMOS gates. In CMOS, we connect P-type and N-type region and made a junction of N-type and P-type material, and we make a complete metal oxide semiconductor field effect transistor. And this is the lecture. This is the end of lecture about FET. We have studied in this chapter about field effect transistor, junction field effect transistor, or MOSFET, and we have studied here the two types of MOSFET: DMOSFET, depletion type MOSFET, and E-MOSFET, which is enhancement type MOSFET. And we prefer here FETs our BJTs because they consume low power, and we can amplify the value of voltage or current in better way than the BJTs. That's why we prefer here the MOSFET than JFET or BJTs. And this is the end of lecture. Allah Hafiz.